Hi. So today we're going to talk about using the derivative as a rate of change. Last time we talked about different basic derivative rules that you could use instead of using the limit definition of a derivative in order to find the derivative of a function. And now we're going to show a really practical application of the derivative. So the derivative can be used as a rate of change, and a rate of change you can think of as your velocity, acceleration, anything like that. It tells you how fast something is changing. So the position function in math, we usually denote that by s of t. So s of t is just your some position function, and a position function just tells you where a ball or a particle or something is at a certain time. So a position function tells you the location of something. Now, say you wanted to be able to find the velocity of that object. Now, you might be interested in two different things. You might be interested in the average velocity of something, and you might be interested in the velocity function of something. So, jumping down here to the velocity function, we usually denote that as v of t, v for velocity, which tells you the velocity of anything at a certain time. And the way that we find the velocity function is we just take the derivative of the position function. So that's something that's really useful to know. And once you get into learning higher order derivatives, we can relate that back to the acceleration of a particle. Now, average velocity, you might have figured out average speed before, and all you have to do for average velocity is you want to divide your change in position, or I'm going to write that out first, change in position, over your change in time. So in other words, you want to take the distance that you would travel and divide it by the amount of time it took you to travel that. So change in time. Now, this can be denoted by other things, different symbols, so you don't have to write out this long fraction each time. So the change in your position we can write as delta, that triangle symbol of s of t, over your delta t. So in other words, your change in the position function over the change in time, which if you're looking over the interval from a to b, it might be s of b minus s of a over b minus a, where t is your starting time, so t1 equals a and t2 equals b. So that's a lot of variables, a lot of letters, a lot of different things to remember. So let's go and do some example problems and see how this works. So I got two example problems for you today. So the first one, if a billiard ball is dropped from a height of 100 feet, its height at time t is given by the position function s of t equals negative 16t squared plus 100. What is the ball's average velocity over the first 2 seconds? So that means that we want to know our average velocity, which means that we need to know how the position function is changing over the first 2 seconds and the time of the first 2 seconds. So we're looking at going from t equaling 0 to t equaling 2, which means that we need to know what s of 0 is and what s of 2 is. So that's really easy. We have our position function, so we can just plug in for 0 and 2. So plugging in for 0, we get negative 16 times 0 squared plus 100, which is going to give us 0 plus 100, or 100 feet, which is good because it tells us that its initial height is 100 feet, so s of 0 should be 100 feet. And doing the same thing for s of 2, we get negative 16 times 2 squared plus 100, which is negative 16 times 4 plus 100. Negative 16 times 4 is just negative 64 plus 100, which is going to be 36. Okay, so now all we have to do is plug into that average velocity fraction, and we'll have our final answer. So our average velocity is going to be equal to s of 2 minus s of 0 over 2 minus 0. And you always want to do your further time minus your initial time, because your delta s, didn't mention this before, so your delta s is really equal to your final minus your initial position. That's what the delta symbol stands for. So you ever take a physics class or anything like that, whenever you see a delta, it means your final minus initial. So we're going to get 36 minus 100 all over 2 36 minus 100 is just going to be negative 64 over 2, which is going to give us negative 32. And now we're not just going to write negative 32 because we had units in our problem. So if we go back and label all of this, we have 2 seconds minus 0 seconds, and this was 36 feet minus 100 feet. So our units of 64 were feet over 2 seconds. So this is just going to be 32 feet per second. Because it's a velocity, so we need units, otherwise the number means nothing to us. Now you might be asking, why is it a negative velocity? It's a negative velocity because the billiard ball is going downwards. So if we think about this as being where our ball is dropped, it's going downwards. And velocity, unlike speed, velocity takes into account what direction your object is moving in. So your speed overall is just 32 feet per second, but because the ball is moving downwards, your velocity is negative. Okay, so let's try an example where we're talking about finding the specific velocity. So in this example, at time t equaling 0, a diver jumps off of a platform diving board that is 32 feet above the water of a pool. The position of the diver is given by the position function s of t equals negative 16t squared plus 16t plus 32. We want to know what the diver's velocity is at t equaling 0, which means that we want to know v of t when t is 2. So that's what we're looking for. Now we talked about before how velocity of t, or v of t, is just equal to the derivative of your position function. So our position function is this function up here, this quadratic here. So let's apply our power rule and all those different differentiation rules that we were talking about in the last video to this function. So for the first one, we're going to apply a power rule. So we're going to get negative 16. We're going to bring down our exponent. So 2 is going to become a coefficient times t to 2 minus 1 plus 16 times 1 times t to the 1 minus 1. And then the derivative of 32 is just 0 by that constant rule. So here, simplifying, we get negative 16 times 2, or negative 32, times t, 2 minus 1 is the first power, plus 16, and then t to the 1 minus 1 power is just t to the 0, which is just 1. So our velocity function is going to be equal to negative 32t plus 16. So now to find the velocity at t equaling 2, we're just going to plug in for 2 and simplify. So we get v of 2 is going to be negative 32 times 2 plus 16. So we're going to get negative 32 times 2 is negative 64 plus 16, which is going to give us a negative 48. And we need to put units on that because it's velocity. It wouldn't make sense without units. So we know we're talking about feet in the problem because of this word up here, and feet per second is going to be our unit. So our final answer is going to be negative 48 feet per second. So that's how you go about using the derivative to find either your average velocity or your velocity, depending on what you know about your position function and your velocity function. So as a quick review, average velocity is just equal to the change in your position over change in time. So that's going to be equal to your final position minus your initial position, all divided by the length of the interval that you're looking at. And then if you want to know the velocity at a specific instance, you find your velocity function by taking the derivative of your position function and plugging in for the time that you are interested in. So I hope this was helpful for you. Have a great rest of your day. Thank you so much for watching.